We spent a little bit of time talking about some of these polar graphs yesterday. And when we graph them, my hope is that we set up a t-chart, choose values of theta, plug those into the equation that they present you with, evaluate for r, and now you've got a point r comma theta, and you plot. Okay. Now there are and that's what you did in Algebra 1, right? For lines, for parabolas. Pretty much everything that we've done so far throughout Algebra 1, Algebra 2, college algebra, the initial time that you saw a new type A function, you usually, first time graphing it, did a t-chart, found some parent function points, and then later you learned little tricks that said, okay, well this is what the nature of this thing all the time, this is the symmetry that exists for a parabola or something like that. So those things are all components to polar form as well. So we can maybe investigate symmetries. We can investigate relationships between, I know if I see an x squared in any equation, and that's the highest power, I automatically know in my mind what kind of graph is going to be yielded, right? Okay. And when I see minus signs and plus signs and coefficients, I have an understanding of how that transforms that curve. Okay. And we spend a lot of time doing that stuff, right? We could spend the same amount of time learning things with polar graphs. Okay, but we don't have that time. And in regards to you needing this stuff later on, I'm gonna go out on a limb here and say probably 99% of us are never going to need polar graphs at another time in our life. Okay, and if you do go into maybe an engineering field where you need an understanding of polar graphs, or maybe later on when we start talking about a complex number and you go into maybe electrical engineering and you need to understand complex numbers, you're going to have instruction on that, right? Does that make sense? Okay, so you're not going to be missing out if we just skim the surface of this stuff. And that's kind of high school math in general, though, if you think about it. Probability. Entire branches of probability. We have an entire course at school for probability. And it just skims the surface of the surface of the surface of probability. Okay? There are entire branches of mathematics devoted to these little kind of snippets of math that we've been learning throughout high school. Okay? Polar functions is another one of those branches of math that we can investigate a lot more in depth than what we do. Okay, I kind of want to just show you a few forms of polar equations. R equals, I didn't do this one with the last class, but if we just say theta, okay, and right now I've just got between 0 and, let's go, 4 pi. Let me zoom out of here. Gives me that curve there. Okay? If I start making that a larger value of pi, it starts to kind of wrap around on itself. And I am in degrees, so let's just do this. Let's go to might have gotten a little carried away with the degrees there. Right, so that's the thing, is that it didn't really zoom in. I think this is kind of what happens when you take 83 or 84 if you get carried away with the degrees, is that it starts to kind of get pretty rigid. So let's do, yeah, that's what I was looking for. All right, so 2160 gives me a spiral, right? Okay. So what that is, R is equal to theta. So what that is means I'm plotting 30, 30 degrees, 40, 40 degrees, 50, 50 degrees. Okay. And when I do that, it creates that spiral. So R equals theta is that curve there. Let's say we've got R, we did this one, R equals A sine of theta. Right now, let's go theta between 0 and 2 pi here. And yeah, I'm zooming out real far. I keep doing this. Let's do this. Let me change to radians. There we go. So we get a circle. Okay. Now that circle, so anything of this form, a sine theta, is going to be a circle that is symmetric with the y-axis. Does that make sense? Okay. And the diameter of that circle is going to be that a value. Is that all right? Okay. So that's kind of one of those relationships that we could learn and investigate so that the next time I get like, when they tell me graph 5 sine of theta, well, I know it's sine of theta, so it's going to be a circle that's symmetric with the y-axis. I know it's 5, so I know my diameter. And because it's symmetric with the y-axis, really, I'm only going to probably graph this semicircle, because then I can reflect that and graph this semicircle. Does that make sense? So those are little kind of practices that you would use to graph these things maybe quicker than just setting up a t-chart. That is one thing to kind of, as we do all of these different types of curves and graphs, is to recognize symmetries. If we find out that that point right there, let's say pi over 3, is what I use for theta. Theta equals pi over 3. And I get back here r equals, so that's 2 right there. So, I don't know, say it says it's like 2.3 or something like that. Okay? If I were to try then, let's try symmetry here. Let's see, theta equals negative pi over 3. If it gave me r to be 2.3, I would know I'd have x-axis symmetry. Does that make sense? It doesn't give me 2.3 when I plug that in, so I know I don't have x-axis symmetry here. But if I tried theta equals 2 pi over 3, that should give me r to be 2.3 again. Does that make sense? Should give me that point right there. What does that tell me? I have y-axis symmetry, right? So that's kind of a check with, if I'm looking at a graph and I'm not sure by the nature of the expression provided, whether it's going to be y-axis or x-axis symmetry, I could do something like that. Okay? If that one point's going to have symmetry, so then the ones around it are going to, therefore we're going to have y-axis symmetry. So those are little things to kind of use and allow yourself to be more efficient in regards to graphing. And basically that's a process of maybe shortening your t-chart. Okay, so you're maybe only going to have to make it twice or half as big as what you normally would. If I interchange sine with cosine, we get something like that. Okay? It's just the same circle, but now it's symmetric with the x-axis, right? Or the polar axis. Changing the a value is going to obviously change that diameter. If I make my a value negative, which is fine, it's now a reflection across this axis here, right? Okay. So there are aspects of that are similar to what we talked about in rectangular systems. When you multiply by a negative, it reflects it over a particular axis, right? Okay. Well, with this, when I multiply by a negative, it reflects it across this axis here. If you were to go back to sine, so you have that circle, if I were to make it negative there, it reflects it across that axis. Okay. So there are those relationships that we would investigate. Is that okay there, right? All right, so now I want to add a to this. Okay, so I have something, maybe right now it's 2 plus 2 sine theta. 2 plus 2 sine theta. Everything that is of that form, where you have some constant, a, plus the same constant times sine theta, you're going to get a shape that looks like that. Okay? If we manipulate the a again, it's just going to stretch it or enlarge it. If I make it negative, it's going to reflect it. But what's that look like? Look like a heart? Okay. Looks like an apple. I usually get a lot of, that one looks like a butt. Okay. But they, the math community says that's a heart. And the word we're going to use is that it's a cardioid. A cardiac, right, for your heart. So that's called a cardioid. Changing the sine to cosine, similar relationship that we had when we were looking at circles. It just switches your symmetry now along the x-axis or the polar axis instead of the y. Does that make sense? So anything of that form is called a cardioid. All right, let's make these two numbers different. Let's make A and that number, let's make it B, so we create another slider here. All right, so obviously if I make them the same, so let's get them both to, well, let's do this. Let's make A 0 and B 1. That would be just 1 cosine theta, right? So that's why we get a circle. If I make them both the same, come on, we get a cardioid. Okay, let's make them different. We get something like this. Okay, it kind of looks like it's not a circle. Kind of looks like one. And if I do this, you can start to see more drastically that is not a circle. So make this B value grow here. What this is, and I can go either way, okay, but we call this little region here a dimple, okay. This shape is not a cardioid, even though it kind of looks like a heart, right? It's not because of the nature of these two numbers being different. We call this a lemma sign. Put that little accent on the C. I think it's Latin, not sure, but it translates to snail. Okay. I don't know. As we adjust and this is the nature of this dimple, and what we're going to see here in a moment is directly linked to how A and B work as a ratio to one another. But eventually, that dimple starts to fold in on itself, and we create what we call a loop. Okay? And that's where it's important as we start graphing these things. If we're to create a T-chart, we would see that this thing would show that kind of movement. Does that make sense? As we graphed it, okay, we're moving around there. We create the loop, and then come out of that loop. Okay, but that's still referred to as a lemma sign. Okay, is that right? There is. I think I showed you this one yesterday, or we talked about it. If I go R equals just A sine of n theta. Obviously, if A is 1 and n is 1, it's a circle again, right? Okay. We end up with 1 sine of theta. That's a circle form. If I make A grow, it's the same idea. So this A, ultimately, with everything that we're doing, this A is kind of a multiplier, right? It's a dilation. Okay, it's stretching it. Now, if I make n, and I want to do it where it gets kind of fuzzy when it's. There we go. I want the step to go by 1. All right. If we start at obviously 1, we get a circle. If I go n to be 2, so this would look like 3 sine of 2 theta. 3 sine 2 theta. We get this shape here. We call that a rose. Okay. It starts to look like a flower, right? Okay. Each one of these branches is obviously it's called a petal, right? Okay. When this number here is even, when the coefficient for your theta is even, you end up with twice as many petals as that number. So there I've got, if we go through and count these, we get 8 petals. If I go 6, there I have 12 petals, right? 12, there'd be 24 petals. Okay. Now, if n is odd, so n being 1, again, we get the circle. But if it was 3, we get 3 petals. If it's 5, we get 5 petals. If it's 7, 7 petals. So we see there the relationship that if your coefficient for theta is even, you get twice as many petals. So that's a nice thing to know, because as I start graphing 1 or 2 petals, and I know I should have 8 of these things total, and there's symmetry, I can probably get those other 6 petals pretty quickly, right? By using symmetry. If it's an odd coefficient for theta, I get that many petals as well. Okay? And there's still some symmetry existing when we have an odd number. Okay? All right, so you saw what was happening when. So you got it set up right now for steps being integers. But we can start messing with this. We start doing these types of things. Have you guys ever, I forget what they're called. We used to have them when I was little. They're little plastic spirographs, yes. Did you hold those ever? That's spirograph. Okay. Those of you that don't know what that is, it's you take like a plastic template, and it's got holes in it, and it works around like you put like a disc or a circular disc in it. It's got like teeth cut out of it, and you just kind of put your pen in a hole and you start rotating, and it travels your pen and it creates that picture there. Okay. Now, last class I kind of showed them this, and I'm going to be straight with you. I don't know 100% the coding that goes into this machinery and the computer work for this. But I would assume that there's a potential for polar coordinates to be used. I do know that there's parametric equations being used, and there's probably matrices and all that kind of stuff in the background of coding something like this. But if you know what a CNC router is, okay, or if you don't know what a CNC router is, I'm going to show you. Okay, so a CNC, you guys know what a router is, right? A router, now, not a router like what's in the ceiling up there, a router for like woodwork. Okay, it's simply a drill bit that moves real fast and carves away wood, right? Okay, or you can do it with metal and stuff like that as well. But a CNC router is simply a router that is placed on rails, and it moves it in 3 dimensions. It moves it left, right, and up, and left, right, forwards, backwards, up, and down. Okay, and it carves out. It has the ability of carving out very precise, intricate designs. Okay, but we have to be able to tell that router how to move. So we create these programs that we can set a design on a piece of wood or a scrap piece of metal or whatever, and we design the image that we want. So this is kind of walking this guy. He's walking us through the image that he wants. He went real fast there. But he wants that image to be carved out of a blank piece of wood. Okay? So creating that image then feeds data to the computer that is going to operate the motion of this router, right? Does that make sense? And that router is going to move left, right, and up and down and forwards and backwards to create this carving. So what happens here, you create this and then you export it as a file, and then you've got your router is going to have another software that reads that file and all that kind of stuff. But let's see here. So this is the router. It's just a drill bit. It's going to be moving up and down here. Kind of show you a little bit of how this works. So you see it's moving towards you and it's moving up and down and cutting things out, right? Okay. So it's cutting out that design using the data that was fed to it. And you know, this one's moving in very kind of systematic left-right movements to cut out this shape, but There are times where it doesn't have to move that way. It can move kind of circular. Does that kind of make sense? But as you work through this, it starts to cut that out, and you've got a very intricate design, right? I would argue that that is probably maybe a place where these types of graphs and these types of coordinates might be fed to that machine to do things a little bit more efficiently than what rectangular coordinates are able to. Okay. Now, with that, if you're in rectangular, you've got an X, a Y, and a Z, right? Okay. And they're referred to, if you've ever messed around with a CNC router, they're called your X-axis, your Y-axis, and your Z-axis. But I would venture to say that there's a potential in the software, in the coding, that somewhere there's probably some work with polar coordinates. Okay, you just get it makes the algebra, it makes the data more concise. So that's a rows. Okay, let's do this. Let's go. This is the way these are always described. Now, Desmos isn't going to know what I mean by this. Okay. So R squared, so your radius squared is equal to A squared sine 2 theta. That's just a really clean way of writing it. But if you click here, it's going to tell me that it doesn't know what this is because it's got to be linear in R, meaning R is going to be raised to the first power. So ultimately, it's telling me that for polar functions, Desmos doesn't have like a native or implicit grapher. Does that make sense? Like if it was X squared, Y squared, that kind of stuff, it knows what to do. But when it's R squared, it doesn't know what to do. Okay, so, the coding just isn't as elaborate for polar forms as it is for rectangular. This type of curve is called a limb skate. And I don't know what that translates to. The other one was snail. But that's that shape. And obviously then you can change. So changing A, obviously, is just like all the other ones, is creating kind of an amplifier or a dilation of this thing. It's going to have origin symmetry. Okay, if you rotate this thing 180 degrees, does it become this kind of pedal here? So that would be maybe a feature that we would use to graph these things a little bit quicker. And if I change it to cosine, it's going to be a very similar thing. But the cosine one is actually symmetrical to the x-axis and the y-axis. So that would be nice because now I was going to graph that. Maybe the only thing I need to graph or use in my t-chart is things in the first quadrant. So when I go from 0 to pi over 2, it's probably going to give me this loop here. Does that make sense? And if I know that it has x-axis symmetry, I create that loop. And if I know it has y-axis symmetry, then I can come over and create that. Those are called limb skates. Okay. And if you change this here to n, obviously it starts to looking kind of like you just get sometimes some weird things. But obviously because that n is not 2, because 2 is when it's the limb skate, you start getting just different types of polar graphs. Okay? Spent a little time earlier just trying to mess around with some things here. And I took these. Now they're complex, messy looking equations, but they're in polar form. And even though they're messy, they're in polar form. Think about how messy that would be in rectangular, then, right? Okay. And the algebra that would be involved in trying to create this graph in rectangular. Okay. But it creates then maybe that image. Okay.
Everything the flat, the center bit. Is that what that outside?
No, I did. So the greater than one. So it's just the Like if I make these equal, it just gets rid of the shading. That makes sense. I don't know why. Oh. There we go. So here's my thought. Like I look at that and I think like embroidery, okay, and I think of like high-end sewing machines being able to, you essentially feed the sewing machine's computer a picture, and you tell it where to kind of embroider on the clothing, and it goes through that, right? I think that would maybe be an application. Think about a sewing machine, it's kind of like a CNC router, okay? I would think that would maybe be an application for these types of things. Okay. If you did a quick Google search, you could find a lot more maybe intricate, interesting looking polar functions, polar graphs. All right. So I just wanted to kind of introduce you to that. When you get to the final, what they'll ask you to graph on that thing and analyze in polar form would be like a circle, like A sine theta, A cosine theta, and then graph that. And we'll have practice of that prior to then. But you're not going to be overwhelmed by those types of questions on the final. All right, but what will be on the final, so I want to spend more time on this, is something called the Moyer's theorem. And in order to address the Moyer's theorem, we have to talk about polar form of complex numbers. In order to talk about polar form of complex numbers, we need to know how to graph complex numbers, which we don't know how to do yet. Okay? So this is getting us into manipulate complex numbers. Now, again, complex numbers are maybe something that's in our use of them. We haven't used them a whole lot in high school math. Maybe just to see that when we multiply a plus bi 2 times, we get a negative 1 for the I squared part, right? We mess around with that stuff. We divide complex numbers a little bit. But application-wise, maybe we haven't seen where we would use these. Like I said, there's a lot of stuff in like electronics, electricity, mechanical stuff that uses complex numbers. So eventually, if you get into those fields, you will obviously have a lot more maybe applicable uses of what we're going to talk about in the next couple days. We're going to talk about graphing complex numbers, polar form of complex numbers, the Moyer's theorem, and nth roots of complex numbers, which is actually an aspect of the Moyer's theorem as well. All right, so graphing complex numbers, this is something we don't know how to do. If I want to graph a number, just a singular number, like 5, I only need one axis, right? I only need one number line, and I need the real number line. Okay? So if I want to graph pi, I need all the values on that number line, right? So remember back to a geometry. We need the ruler postulate, one number line, and we can graph then any point that we want, any one-dimensional point, so like 5 or 12 or pi or radical 3, we can do that. Okay? Complex numbers, that provides us a problem because complex numbers have 2 components in them, right? They have an A, which is a real number, and they have your BI, which is the imaginary number. Okay? And this format of complex numbers is what's beneficial in fields of like electricity, because they talk about resistance and current and stuff like that. And there are a lot of times the need to show, especially with resistance, I believe, 2 characteristics about that idea or that property with one number, A plus BI, or one representation, A plus BI. So the A part in electricity, I don't know what it means for resistance, but the B part then means something else for resistance. Does that make sense? Okay. You guys know what resistance is in electricity? All right, so the wires and stuff like that that you use will eliminate or will start to make your electrons kind of diminish, right? So if I have like a 9-volt battery in a 2-mile long piece of wire, the electrons are not going to travel through that wire, right? Okay. They're gonna fade out at some point. If I have a 9-volt battery and a 2 centimeter wire, the resistance is not going to. I'm going to have flow through, and probably too much flow, right? Probably short circuit things. All right, but complex numbers, however, have two components: a real part, and imaginary part. It says this suggests that we need two axes when we want to plot one of these things, and we want to graph a complex number. So what we end up with is a real axis and an imaginary axis. Okay, and that determines what we call the complex plane. Okay, so give you a picture here of what the real axes and the imaginary axes kind of look like. Looks like that. Okay, but this a lot of times we just say is RE, and we call this IM. But it's just like your X and Y's, right? Okay, this is going to be how we plot or where we plot our A values, and this will be where we plot our B values. Let's put my I there, my BI values. Okay? So when we have two components then for a complex number. So here's the thing. 3 is a complex number, right? It'd be 3 plus 0i, and we can plot that. It'd be right there. That's normal, right? That's how we would plot 3 on just a one-dimensional number line. I can do that with any number that is just one-dimensional. Okay? Now if I wanted 3i, okay, that's now there. Does that make sense? This is my imaginary axes. I have 0 real values, 3i, 4i, 1i, negative 1i. Okay? But what if I want 3i plus 4? I'm actually going to write 4 plus 3i. What you do is you go 4 in the real axis, followed by 3 in the imaginary axis, and that ends up being your point. That's where you plot it. Okay? That's why it's called a plane, is because it's now two-dimensional, right? That's what planes are. Okay? You move left, right, and up and down. And so, kind of analogous to, it's not the same thing, but analogous to X's and Y's, this would be like kind of your X value you move left and right with, right? This would be your Y value that you move up and down with. And then you plot those points. Now, notation-wise, whenever we talk about a complex number, I don't know the reasoning for this, but we call it Z. So this is the point Z equals 4 plus 3i. Okay, eventually what you're going to see is the next thing we do with graphing complex numbers is that we start at 0, 0, and we're going to draw out to that point a directed line segment, a vector. Okay? And there's going to be some things that we're interested with there. Okay? Firstly, we're going to be interested in the length of that thing. Okay? Well, the length of that thing, isn't this going to be 4? And that's going to be 3? Is there a right triangle here? So the length of this thing is going to be the square root of whatever your real component was squared, plus whatever your imaginary component was squared. When I do the imaginary, I don't incorporate the I. Okay? Just the coefficient for it. And we call that then, let me move that so I have a little bit more room here. We say it's the absolute value of Z. Okay? It's the absolute value of A squared plus B squared taken the square root. So it's just the distance, right? Does that make sense? Okay. We call the absolute value of Z the modulus. And now there's several places in mathematics that we use the word modulus. If we have time later on, we'll do a little bit of work with that. Maybe those of you that are here after the seniors leave, maybe we'll mess around with some hit and miss, like discrete mathematics concepts that but we maybe use it. So modulus a lot of times refers to what's left over when you do division, the remainder. That makes sense? So here, though, we're using it as the word for the distance of that thing there. And if you are in physics, you might remember that being called the magnitude of that vector. Okay? And you use the same symbolism. I don't know if that's a word. Symbolism? Is that a word? Symbolism? Yeah. Sound right? It doesn't sound right when I said it, though. That notation there, okay, is what you use when you did magnitude, right? Okay. Now, thinking about this, is there, if that's starting at 0, 0, and it ends at this point here, is there a circle that would be centered at 0, 0? Okay. So, eventually, we're going to say that that is the same thing as R. Okay, so 4 plus 3i. Think about how we plotted that. We moved right and left and up and down, right? When we graph complex numbers like 4 plus 3i in a complex plane like that, we are moving rectangularly. That's a rectangular version of a complex number. Well, sometimes it might be more beneficial to move at an angle along a certain modulus. Does that make sense? Or along a certain vector. So there is an aspect of moving these things into polar form. This theta here. Okay, that would be theta, right? Could that theta be found by taking tangent inverse of 4/3? Or not 4/3, what I got? 3/4. Sorry, I messed it up. 3/4. Last class we did 4/3. So if I do that tangent inverse of 3/4 gives us 36.8 degrees. Okay. Wouldn't this distance here be 5 if we end up going through that? 4 squared plus 3 squared, your modulus would be 5. Okay. So the fact that theta is equal to 36.8 and r would be 5, that would be a set of directions that allow us also to plot that blue point, 4 plus 3i, but doing it in polar form. Does that make sense, everybody? Now there's a way that we're going to use notation here in a moment to address that and to do that accurately. If we let's just look at this PowerPoint real quick. Go to this slide here. So we find absolute value for complex number this way. Square root of a squared plus b squared. We've got that. We've done that. This identifies the modulus. Okay. Here in parentheses, or absolute value. So that's the kind of way that we're interpreting the modulus here. Of the complex number is that thing right there. And that's that length of that vector. Okay, so there will be questions when they ask you to find the modulus of this complex number. All you gotta do is take the a part squared, take the b part squared, add together, square root. Okay, should be pretty straightforward, pretty easy to do that. There you see 2 examples of that. I'll let you guys go through that on your own. But here's where I want to take this information that we just kind of showed on that GeoGebra. With every complex number that we graph, we should be able to come up with a right triangle. We should be able to come up with theta then for that right triangle. Okay? Now, this distance here would be b, this distance here would be a, right? If I look at theta, we find theta by taking tangent inverse of b over a. Okay? If I look at theta again and I say cosine of theta, by definition, cosine of theta would be a over r, right? Well, a over r turns into r cosine theta, gives me a. Does that make sense? That's key for us. Because a is your real number and it is now equal to r cosine theta in polar form. Does that make sense? Sine of theta is equal to b over r. Multiply both sides by r, I get that. Okay with everybody? So now let's make some substitutions. If I have a plus bi, that's rectangular. If I put in a to be r cosine theta, and I put in b to be r sine theta, so a right there plus b right there times I. We can now have, that is what we call the polar form. Now that polar form a lot of times isn't written that way because they both have an r in them. So they usually take the r out and they go cosine theta plus, now I'd have sine theta times I, right? Now to eliminate the potential of I being part of my argument, they always put I out front of sine. So they go I sine theta. Come on, I sine theta. And what you're going to find out is that that's the way most of the time we write polar form inside WebAssign. But by doing things by hand, that is still messy. So what they do is this. They go R, and then they just start taking acronyms basically here for the rest of it. So C stands for cosine. The I stands for the imaginary component that attaches itself to sine. So we use S, and then we put our theta. So R, we read that R cis theta. So that question we were doing, R was 5, right? Theta was 30, was 36.8, something like that. Okay? That is the polar form of 4 plus 3i. And the benefit of this right here, guys, is going to be eventually, when I want to take 4 plus 3i and raise it to the 10th power, that's a pain in the butt right here. Put over here, raise it to the 10th power, I'm going to tell you it's 50 cis 360.8. Okay? I'm sorry, 360, not 360, 360. It's really easy. It's not 50, it's 50 to the 10th power, sorry. It's really easy to take a polar form of a complex number and multiply it by itself, or even multiply it by another polar form complex number than it is to take two complex numbers and multiply them in rectangular form. So that's the benefit of this. So we'll work on Monday. We'll rehash this slide. We'll go over this again. I know it's going to be 3 days, and we're going to forget. So we're going to talk about this again on Monday. We'll do a couple examples, and then that will introduce us into that de Moivre's theorem that is actually the process for multiplying complex numbers.
Just a reminder that all seniors will report to the gym for walkout time for a